In this video, we present our work, RTSGameBench, an RTS benchmark for strategic reasoning by vision language models, through gameplay demonstrations and a self-evolving game generation framework. First, this is a full game video of a 1v1 matchup, edited to highlight key moments that are important for victory. Next is a team matchup played on a larger map, where the green units represent the agent we control and the blue units represent its ally. Next is a 3 versus 3 matchup, where the purple units are also part of our team. The game takes place on a larger battlefield, resulting in longer matches and more frequent decisions. This is an asymmetric 3 versus 4 matchup, where our side has one fewer team. It demonstrates how the agent adopts a more defensive strategy in an unfavorable scenario. This matchup is a free-for-all between 4 teams. The agent first defeats the nearby red opponent early on, then eliminates the yellow opponent to secure the final victory. Next is a minigame. This is the time-constrained production scenario, designed to measure resource management ability, where the agent must produce a welder unit while withstanding enemy interference to win. The multi-front defense game, designed to evaluate spatiotemporal reasoning, requires the agent to defend 3 points. The game is lost if any one of them is destroyed. The fixed-field FFA game, designed to evaluate opponent modeling, features 4 teams fighting until only one remains. The controlled agent is the blue team. The fixed-field team game, designed to evaluate collaboration, uses the same setup as the previous game, but changes the format to a team match. The agent is green, and its teammate is blue. The siege planning game, designed to evaluate adversarial planning, requires the agent to locate and destroy a hidden target under fog of war by scouting and advancing through enemy defenses. This is workflow of our proposed self-evolving minigame generation framework. First, the designer clarifies the user's intent through multi-turn dialogue and produces a scenario brief describing the game setup, enemy behavior, and end conditions. The framework then searches the GDD database for a matching game design document. If one exists, it skips directly to the final script generation stage. Otherwise, it generates a new GDD. Next, the designer expands the brief into a full GDD, and the analyst validates it against rubrics. If it fails, the designer refines it using feedback. Once the final GDD is obtained, the framework proceeds to the rule set generation stage. Then, the developer implements the rules as Lua scripts, reusing verified rules when available. The analyst validates the rule set through rubric-based checks and simulation. If repeated attempts still fail, the project manager analyzes the feedback and provides meta-feedback to guide further refinement. Based on meta-feedback, the developer and analyst repeats the current stage and successfully produces the rule set. Finally, the developer specifies configurations to generate the executable minigame script. The analyst evaluates it through rubric-based checks, and a VLM verifies gameplay screenshots for visual playability and semantic alignment with the original query. After generation, the project manager updates the rubrics and stores the validated GDD and rule set in the database. By reusing these accumulated artifacts and feedback in future generation, the framework continuously improves over time. That is what makes it self-evolving. The final generated game, Kite or Die, is a new mini-game where both the agent and enemies die from a single hit, designed to evaluate the agent's ability to perform precise kiting under extreme risk.